One. Hello, AP Chemistry, and welcome to, okay, so this is more of 17.3 titrations. And here we're going to talk about a different kind of titration. So here, if we look at this curve is definitely different than the one we saw previously, okay? So if we look here, right, we start at a pH of 3, right? So this is still the same basic idea, right? This pH is our initial pH, which represents just whatever we start with, right? So this means we're starting with an acid that has a pH of 3, which, assuming it was the same concentration as the one before, which it is, right? That would mean that this is a weak acid, right? Because it's not completely dissociated, so it starts off at a higher pH, all right? Now, you'll see here, right, that this rise, right, which goes from about 0 mils up to almost the equivalence point, right? So let's say 48 mils, right? Now, instead of last time it only went up 1 pH unit, now it goes up from 3 to 4 to 5 to 6, right? It moves several pH units more gently, okay? And that is one of the characteristic signs that we're looking at a weak acid titration or a weak base titration, okay? Note that my titrant is still a strong species, right? Because a weak species does not react completely, right? It doesn't react completely, so if I took 2 weak species, we couldn't generate a titration curve, right? But here, right, we have a strong base, which means that that base, every time we add it, will react completely with however much equivalent moles of acid are present, okay? So here is where we get this gentle rise. Now, this part is really, really important because when we're talking about a weak acid titration, this is also referred to as the buffer region, okay? Because one of the simplest ways to make a buffer is to just partially neutralize an acid or a base, okay? One of the simplest ways to make a buffer is to partially neutralize a weak acid or a weak base, right? So if we think about what that means, right? So here we're starting with acetic acid in solution, right? So we have some acetic acid in solution and we add some NaOH, right? Means that we're going to produce some, what? Right, NaCOO plus H2O, right? Which means that we will have some HA and A minus in solution, yes? Those being the keys to having a buffer system, right? Thinking back a little bit, right? Actually, let's just write it out this way. HA over A minus equals our H3O plus, yes? Right? So then, when we look at this, right, this going back to our K expression rearranged, so that way we can look a little bit more closely sort of at our pH, right? So here, if we think about this, right, so we start off with just HA in solution, and as we add our sodium hydroxide, we slowly but surely produce some of my A minus, right? And eventually, we actually reach a place where HA is equal to A minus, yes? We eventually reach a place on our titration where HA is equal to A minus. Where does that happen? Right. That happens at the half neutralization point, right? So here, if neutralization happens at 50, then at 25, we have our half neutralization. And at our half neutralization, right, this scenario exists, right? At our half neutralization point, the concentration of HA equals A minus, yes? Because I've neutralized half of this, which means that I have equal amounts of this and this, yes? All right, half neutralization. If I think about that, when this concentration equals this concentration, my Ka is equal to my H3O plus, yes? When the amount of HA is equal to A minus, my Ka equals my H3O plus, which means that this allows me to deduce the Ka of a weak acid, right? Which is actually one of the reasons that you would titrate a weak acid. So here, right, I know that's not straight, but that's approximately what? Let's call that 4.3, right? So that means if my pH is equal to 4.3, that means that my Ka is equal to, right, 10 to the negative 4.3, yes? And I know that courtesy of the half neutralization point on my titration curve, yes? All right, let's talk about other important points. So here we have our actual equivalence point, right? So again, this is the volume, and this is my pH. What do we notice? Right, this is a pH of about 8.2, as opposed to being at pH 7. So let's talk about what species are present. So, do I have any of my original acetic acid? No. Do I have any of my sodium hydroxide? No. What do I have? Right, I have sodium ions, I have these ions, and I have some water. What do I notice when I look at those three ions? Right, this is the conjugate base of a weak acid, which means it's basic. Yes, this has a tendency to take protons from water, increasing the amount of hydroxide in solution, giving us a basic pH at our equivalence point. Yes? All right, fantastic. If need be, think that over a couple times and make sure that makes sense. All right, here we note, so again, original pH based on just my weak acid. Here we get our buffer region, which is a slow, gentle rise in pH as we create a buffer system. And eventually we get to our neutralization, right, or our equivalence point. And you'll see that here it's a really small window, right? A really small window, unlike our strong acid, strong base. And then after we reach the equivalence point, all of the pH is determined by my excess titrant. Yes? Fantastic. All right, let's compare a couple of important notes. All right, so here it says that we have 50 mils of 0.1 molar acid with 0.1 molar sodium hydroxide. So this is 0.1 molar sodium hydroxide, and these are all 5 different acids that have a concentration of 0.1 molar. Okay, so note that when I take 0.1 molar acid and 0.1 molar base, regardless of the strength of that acid, all of them have the same volume for the equivalence point, yes? Because these concentrations are what determine the number of moles present, yes? And the number of moles are what's determining how many mils of my titrant have to be added, yes? All right, so then we have our titrant, and those all happen here. The only difference is, right, the pH at that equivalence point, right? So the pH of that equivalence point. And we'll see that the weaker my acid, the higher the pH at my equivalence point, right? And we know that these are weaker because this pH keeps going up, which means that my initial acid is weaker and weaker, right? And if we think about what that means, the weaker my acid is, right? Let's write this out. So my weaker acids will have what kind of a K value? Right, we'll have smaller Ka values, which means, right, by extension, a larger Kb value, which is why this, which is basically its opposite, right? This pH is governed by my weak acid, or strong acid in this case. This pH is governed by the conjugate base, right? The more basic that conjugate is, the higher this pH is going to be. Yes? All right, fantastic. Make sure all this makes sense, digest it a couple times as needed. In the next one, we'll talk about a little bit of math dealing with weak species titrations. All right, thank you for listening. Be good, and I'll see you soon. Bye.